Hello everyone, welcome back to my tutorial series on the topic of statistical analysis in Python. In the last tutorial, we covered the topic of descriptive statistics, and now let's focus on learning a little bit about data distributions and of course going through a few slides to get the background information and then jumping into Python. The future tutorials, of course, in this series will be focused on statistical analysis, and we will cover different aspects in each of these sessions. So please do subscribe, pause right now, subscribe to this channel if you are interested in these topics. While you're there, find the little thanks button in case you're feeling extra generous. Okay, so what are we going to do in this tutorial? Well, let me proceed to the next slide. We are going to learn about normal versus non-normal distributions and how do we test for normality, because normal distribution is a prerequisite for certain statistical tests. So it is important to know how to test for normality. And if they are not normal, if the data is not normal, what type of data transformation techniques are available, and also learn about when to transform data. All of this we're going to apply on a wine quality data set. And whatever I'm showing, of course, these are statistical concepts, so you can apply to any type of statistical, any type of data. But wine quality data set is something we all can easily access, and I'll briefly talk about what it is in a minute. But first, the normal distribution. If you look at the plot on the right-hand side, this is something that you probably the type of curve that you would see. It's also referred to as a bell curve. Bell-shaped, symmetric around the mean. As you can see, mean is the center right there, and it's symmetric around the mean. And typically these are characterized, not typically, usually they're characterized by mean and standard deviation. Mean with the symbol mu, the same symbol we use for micron, and standard deviation with a lowercase Greek letter sigma. And the key properties are, when you look at these normal distribution curves, about 68% of the data falls within one standard deviation, 95% of data falls within two standard deviations, and 99.7% of data falls within three standard deviations, which means basically plus or minus 3 sigma, right? So total 6 sigma. Within the 6 sigma, you have 99.7% of the data. So these are the typical characteristics of normal distribution. And of course, why is it important? It lays the foundation for many statistical tests, like I just mentioned. It's a requirement for parametric tests that assume that your data is normally distributed. So whether you're performing t-test or ANOVA test or linear regression and so on, it assumes that your data is normally distributed. And what are the common non-normal distributions? So on the left-hand side in the graphic, you see the normal distribution from the previous slide. On the right-hand side, there is just a horizontal line. It's just a uniform distribution, which means all x values have exactly the same y value. In this example, 1.0. That's normal distribution, so there is no central tendency. It's just everything has pretty much the same value, all x values. So, and the other example would be exponential distribution. So it just goes down exponentially or goes up exponentially. And in this example, it is highly right skewed, as you can see. And log normal distribution is, again, as the name suggests, it's a logarithm and normal distribution, almost like combining these two. And it is right skewed, so you see positive values right there. And the other is bimodal distribution, so you have like some sort of a normal distribution, another normal distribution, and there is a connection between them. So this is bimodal. You have two frequencies here, high frequencies. So these are the common ones. And how do you test for normality? For example, if I have some sort of a data distribution, how do I know it's normal? Well, obviously, visually you can tell, right? I mean, you can see, you can tell, okay, that looks like normal distribution, but maybe you need quantitative ways. So you can look at the histogram. I mean, you plot it and then you apply like a smooth histogram on top of it to look at the shape. And of course, if it appears like bell-shaped, and then you can tell it's possibly normally distributed. And of course, as you change the histogram width, the bin width, then the shape may change, right? So you have to be careful about that. And a better way is QQ plot, quantile plot. And a quantile is basically the percentage below which you have all certain type of data. For example, if you have a quantile of 0.3 here on the y-axis, you see a value of 0.3. So if you look at this data point right there, it basically tells you 30% of the data falls below that specific quantile, and 70% of your data falls above that specific quantile. So a quantile plot, it plots the quantiles against a theoretical normal quantile. What that means is if your data is normally distributed, which means it has normal distribution, bell-shaped, perfect bell-shaped would fall along this red line. That's the theoretical value. Obviously, this is not doing that. That means it's not, it's doing it partially. So you can tell, oh, well, it kind of partially is normal, but then something's happening right around there. So, but definitely it's not normal distributed. So using descriptive statistics, which is your plots like these, you can kind of infer what, whether this is normal or not. You can also look at box plots. In a way, you can infer whether it is normal or not. Like if this box is symmetrically centered, if this line is symmetrically centered around this box, that suggests some sort of a normality. And if the whiskers are approximately of equal length on both sides, for example, that suggests that it is probably normal. Now, there are two other metrics like skewness and kurtosis to measure normality. I'm saying measure. I'm not saying quantifying normality. These are two methods to measure, which means they are still based on descriptive statistics. So skewness is a measure of asymmetry in the distribution. Is it positive? Is it negative? Is it zero skew, right? So positive is the tail extends all the way to the right, and negative is tail extends all the way to the left. And it's basically the data is skewed one way or the other. And kurtosis is a measure of tailedness. Like basically, it tells you more about outliers. A positive means you have very heavy tails. There are more outliers than normal. Remember, we're comparing everything to be perfect normal distribution, perfect bell curve. So there are certain tails, but the amount of data that you have in these type of tails, like how long the tail goes on, that kind of can be reflected by kurtosis value, and it can be positive, it can be negative. Negative is light tails, which means you expect certain tail, but then the data abruptly stops, right? So that means there is not much of a tail, and that gives you negative. And zero is similar to normal distribution, which means, hey, it follows a normal distribution. So kurtosis can be a good measure of normality. Again, here I'm showing you a typical output. And ignore the Shapiro-Wilk. We'll talk about that literally in a few seconds. And if you look at the skewness and kurtosis, you see certain values right there, right? So based on this, you can say whether it is right skewed or if there is any kurtosis, let's say, in this specific data set. Okay, and both of these are descriptive statistics. Again, it's describing how the data is spread or distributed, but it doesn't tell you anything about it's not an actual test to test for normality. Okay, so there are certain tests that are and I'm going to talk about a couple of them. One is Shapiro-Wilk test, which is again, any of these tests, whenever we talk about statistical test, we have some sort of a hypothesis and a p-value or something equivalent to a p-value that tells us how much to believe in that metric that you get from that specific test. In this case, Shapiro-Wilk test, the null hypothesis basically says data comes from a normal distribution, which means you are given certain data. The first hypothesis is, yes, this data follows normal distribution. And then you apply a test. And if the test actually fails in a way, then it is not normally distributed. So Shapiro-Wilk is one of those tests, and it's best for smaller sample sizes. And the key point here is based on the correlation between data and corresponding normal scores. It's actually, that's what it's testing. And the output is a test statistic. I mean, Shapiro-Wilk test, if I go back to the screen, you will see that Shapiro-Wilk test statistic value is 0.9411. Now, if you ask me a question about what does that mean, like, does that mean it's normally distributed or not? The value itself, I don't think you should put a lot of focus on it. It's the p-value that goes along with this value. Please watch my last tutorial about p-values. But if the p-value is typically below 0.05, then you can say that, okay, then the null hypothesis has been disproved, which means in our case, the data is not normal distribution. This may be confusing if you're doing this for the first time, but if you're not doing this for the first time, you may be thinking, why is this guy spending so much time on this? Because the first timers can struggle with this concept of null hypothesis. And looking at the data metric, we are usually used to looking at the data metric and making some inferences based on that. You can still try to do that. But the key point here is p-value is very important. If the p-value is below 0.05, typically we say the null hypothesis has been disproved, which means whatever the hypothesis, in this example, data comes from normal distribution is the hypothesis, then the data does not come from normal distribution is what the conclusion is if it's below 0.05 of p-value. So that's what that is. And the next test is Anderson-Darling test. And again, here it places more weight on tails of these distributions. So if you are trying to detect deviations in the tails, like one data set, I mean, basically how it differs from normality, this can be a good test. And again, it outputs a test statistic. And instead of p-value, it outputs critical values at different significant levels. We'll see this in once we jump into the code, and it does work well for large data sets. Another test that I kind of rarely think about is the Agostino-Pearson test. And here it tests for skewness and kurtosis simultaneously if you don't want to do these separately for whatever reason. And the test, it outputs a test statistic and p-value, just like Shapiro-Wilk test. So you can look at the p-value and say, oh, this is basically disproving hypothesis or confirming your hypothesis. Data transformation is something you may have to apply when your data is not normal, for example, and then you want to perform certain statistical tests. As I mentioned earlier, a lot of statistical tests assume that your data is normally distributed, for example, like t-test. And if the data is not normally distributed, for example, you perform Shapiro-Wilk test and you say, hey, the data is not normal, then what do? Well, you can transform your data to make it kind of normal. It may actually work, right? So make data more normally distributed is one of the primary reasons why you would like to transform the data. And you want to equalize variances across multiple groups. You have different groups and they come with completely different variance, and you want to equalize all these variances, then you can apply some sort of a transformation, and a few other reasons you can see right here. Now, what common transformation techniques do we have? Logarithmic transform. So going back to the data I showed you earlier, if you apply a log transform to this, it may actually bring everything to a normally distributed space. And log is basically, you're just applying logarithm to your x. Yeah. And of course, it's very useful if you have data that spans multiple orders of magnitude. For example, if you have data that goes from 1 and 10 and 100 and 1000, right? So then it's, if you want to bring them to a uniform, like a normal scale, then just apply log transform. Then your ones will be zeros, right? Log 1, and then tens will be 1, and hundreds will be 2, and so on. So they all come into a specific range. Now, square root, again, it's just a square root of your x values, and they're good if your data is moderately right skewed, not severely right skewed. If it is severely right skewed, then log would be a better option. Okay. And in fact, the best thing to do is apply a few of these transformations if you don't know which one is appropriate, and then perform a normality test and use the one that gives you the best normalized data. Again, it depends on individual's situation. Now, moving on, the other couple of transformations of reciprocal transform, it's 1 over x. I can't even think of a good example. Time to complete tasks is one example, but usually rarely used, at least in my scenario, when I try to analyze any of the scientific data or even financial and accounting data. Box cost transformation is, it's almost like it's this equation that gives you different types of transformations. For example, when lambda in this equation, when it's not 0, then y equals to log x is how this is defined, which is basically a log transform. Right? Y equals to 0 corresponds to log transform, like I just mentioned. 0.5 corresponds to square root transform, and 1 means there is no transformation needed here. Yeah. So this is another transformation that you have at your disposal. And another one is quantile transform, and it's got to be careful with this one for a couple of reasons. First of all, what is quantile transform? That means in a way, it forces data into specific distribution. It's almost like you have your data and you say, hey, I want this data to be distributed in a Gaussian way. So it's definitely going to be normal distributed. Like you say, hey, I want this data to be normally distributed. So you're changing the data such a way that it fits the normal distribution. So it's almost like mapping your data into a specific distribution. So it of course, it's very effective for any continuous because you're forcing it to be normal. But so, of course, it's guaranteed to produce the desired distribution, because all the other ones like log transformation, they're not guaranteed to give you a perfectly normal distributed data, but it brings you close to that. But here, you're kind of guaranteed because you're reshaping the data to follow whatever distribution that you mentioned here. Which basically means you're distorting the relationship between variables. So, and also making unit interpretation very difficult because you're kind of squeezing this data into a different shape. So be careful when you use these. And in terms of when to transform your data, we all kind of discussed this. When your tests require normality, when your existing visualizations are hard to interpret, when your data goes multiple orders of magnitude, typically bringing them into a log scale kind of gives you a nice, easily interpretable plots. And yeah, equal variance is needed. So we already discussed that. Don't transform when, of course, your original scale is very important for your interpretation. And when you're performing non-parametric tests that do not require normal distributed data, and also the transformations, when they don't improve your normality, there is no point in applying that. And of course, if the data is already kind of normal distributed, then there is no point of distorting them by applying any type of transformation. Now, before jumping into code, I just want to summarize the data set that we're going to look at. It's again one of the UC Irvine data sets, and this one's called Wine Quality Dataset. And one of the famous ones, like the ones, for example, heart disease data is something we worked with. And similarly, wine quality is another data set that machine learning enthusiasts would like to explore. And it contains physiochemical properties of red wine samples. What do I mean by that? It has acidity measurement. It has residual sugar. It's got the chloride, sulfur dioxide density, pH, alcohol content, and what prediction is basically, or the output is quality, right? So if you're doing machine learning experiment, you're trying to see how can quality be modeled or predicted based on all these other attributes, including acidity, residual sugar, and all the other ones. And the quality is between 0 to 10. You're basically ranking wine, how good it is, between 0 to 10, and then these are all the attributes. Okay, so we are all set to jump into the code. So let's go ahead and open our Colab and walk through the code. And by the way, the link to the code is down under the description, so you can just go ahead and explore this on your own time. I tried to add as much notes as possible, so you can follow along and not look at the presentation. So hopefully this should be very educational for you, this specific notebook. Okay, so let's go ahead and import our libraries as usual. The key libraries are going to be pandas to handle our data frames, NumPy, matplotlib for plotting, seaborn for plotting, which works on top of matplotlib. And the key one in this specific tutorial is the SciPy library. In fact, the stats part of the SciPy library, and stats actually gives us a lot of tools. All the discussion about various tests for normality and everything, it's just a one line of code, and we are just plotting them to get better information. And also in scikit-learn pre-processing, there are certain methods that can be very useful, like power transformer, quantile transformer, so we can see how the transform data can, how to transform your data. So we're going to use these to transform the data. Okay, so let me suppress certain warnings and also set the style for our seaborn plotting. And the data can be downloaded directly from here, and it's CSV. So we are directly reading using pandas.csv, and let's go ahead and print out the first 5 rows of this data. So as you can see, it's got fixed acidity, volatile acidity, citric acid, a whole bunch of attributes, and finally what the quality is of that specific wine. For example, number 3 here gives you a quality of 6, or tagged as quality of 6. Okay, so you have a good understanding, and again, descriptive statistics is something I talked about in the last tutorial, but every time I get a new data set, I go through these steps. I have a quick look at it before doing anything, and then I get like a quick information about this pandas, whatever the data frame.info, it gives you, okay, I have all the floating point numbers except the quality, which is an integer. Of course, it goes from 0 to 10 or 1 to 10. That gives me an idea of whether to transform something, but in this case, so far, no. But let me also check if there is any missing data. Looks like there is no missing data, so I don't have to do anything from that point. And now descriptive statistics, just look at various statistics. For example, we have 1599 rows, and the for acidity for each of these, and the mean value for fixed acidity is 8.3. I have no clue what to do with that information because we're not wine connoisseurs, or we don't know what these are. We are not scientists researching wine. So most of these values don't make sense to us, I would assume. And the only thing that where we can actually relate to is the quality maybe. So the mean quality is 5.6 and standard deviation is 0.8 and the minimum value is 3. So the worst wine is rated 3, the best wine rated 8. And here is the different percentile information right there. Now, to understand normal distribution, the first part here is I'm just plotting a theoretical normal distribution so you can have a look at how it looks like. And for that, we can use scipy.stats normal distribution like .norm and .pdf. And whenever you see PDF, you often see these in these exercises. That basically stands for probability density function. Yeah. So we are basically plotting a normal distribution, and I'm just generating x values between -4 to 4, 1,000 of them, and my y value is nothing but applying a norm.pdf probability distribution function normalized normal on this x data. That's pretty much it. Rest of it is just plotting them, and also plotting the lines where we have 1 sigma, 2 sigma, and 3 sigma. So visually we can confirm, look at it, these data points. Okay, so here is exactly what we just plotted. As you can see, there is some tail, and these tails go to infinity, minus and plus, theoretically. And within the green bars right there, you have 68.27% of your data falling within this region, within this green. The red is just the mean. Okay. Within the yellows, you have 95.45% of your data, and similarly within these whatever that color purple, you have 99.73% of all data falling within these regions if it is normally distributed. In this case, it is, right? We are plotting a synthetic plot right there. This is just a bunch of printouts, print statements mentioning exactly what I just mentioned. Okay, let's now actually look at the real data. And instead of plotting all, let's just pick a few columns that we can analyze, like the amount of alcohol quantity in the wine and the pH values and density, residual sugar, and fixed acidity, at least to some, even from basic chemistry class, we know what these mean. And here is a function to check normality. What are we doing here? Well, first, we are actually doing a bunch of plots. So visually, we can verify if it's normal or not. And I'm plotting a histogram plot from Seaborn, bunch of histograms. And on top of that, I want to overlay the smooth histogram. In other words, I'm allowing the kernel density estimation equals to true, KDE equals to true, would overlay that smooth plot on top of our histogram plot. So that's what that's doing. Anything else? I don't think there is much else to discuss. Well, there is qplot, QQ plot, and for that I'm using stats.prob plot, and I'm plotting these values and whatever the values are that we're going to pick, and that's actually going to be plotted right there. And why are we plotting that? So we can overlay onto a theoretical QQ plot and see how our distribution is, if it's normally distributed or not. I'm also plotting a box plot. Again, these are so easy, I even don't want to talk about them individually, like SNS.blocks plot, right? So you just give it X and Y values and that's it, you're done. It's that simple. SNS is again our Seaborn. The next thing is I am going to plot skewness and kurtosis. These are just bar plots showing the values, which means I need to calculate the values first. So skewness is, remember we imported stats, and literally within the stats, scipy.stats, you have something called a method called skew that you can apply on the values, whatever the values are, alcohol content or whatever you pick, and it gives you the skewness of that specific data. Similarly, kurtosis is printed here, and I'm just doing a bar plot of those, and later on I'll just print those specific values, and I have added a few extra print statements so we can easily interpret from the output. So let's go ahead and run, and let me go all the way to the top so you can see what's going on. So let's look at the first plot. And normality analysis for alcohol here. So this is basically the alcohol content, one of the columns that we picked. And you can see it's kind of skewed towards the right, meaning you have some data on the right-hand side and the actual peak is towards the left-hand side. So visually, we can tell, well, probably that's not normal distributed, right? So we will quantify that in a minute. And also visually, when you do QQ plot, if it's actually perfect normal distribution, it should lie along this red line, but this isn't lying along the red line, you know that it deviates from normality. Very simple. And now when you look at box plot, again, you see the asymmetry in these whiskers, a shorter one right here, a long one right there. That of course tells you that it is skewed towards one direction compared to the other. And also this median is not exactly in the middle of this box. That's another indicator that it's not normal. And skewness and kurtosis, I just plotted them, but it does, unless you compare them with other plots, actual values at this point do not make much of a sense, but this should make sense. The Shapiro-Wilk test statistic is 0.9288 with a p-value of 0.0000. It's probably extending to a couple more zeros and then the sub-value. I'm only printing the first 6 decimals right here. And of course, this is much smaller than 0.05. We are going to reject our null hypothesis, meaning our data is not normally distributed. And again, note that our null hypothesis is nothing but the data follows a normal distribution. So we say our hypothesis is data follows a normal distribution. We disprove that because we have a very small p-value for Shapiro-Wilk statistic. Now, the next test would be Anderson-Darling test, and here our statistic value is 34.9171. Again, I have no clue what that value is unless I look at p-values, right? So, but for Anderson-Darling, we don't have p. We actually have critical values that it reports. And I chose to report critical values at 1%, 2.5, 5, 10, and 15. You can add more, but these are the ones we are printing. And the value here, 0.57, compared to the statistic is much small. Meaning we can reject our null hypothesis. Even at 1%, we can reject hypothesis. And at the end of the day, all of these are statistics are, critical values are less than, I should have printed it the other way. The critical values are all less than the statistic. So we reject null hypothesis. By the way, if you do go 25, 30, 45%, the value is going to be much smaller and smaller and smaller. That's why I printed 1%. So even if its statistic is, the critical value is this small for 1%, then it's going to be smaller for as you increase this. That's the whole point right there. And similarly, skewness and kurtosis, again, I want to remind you, skewness and kurtosis, you can infer something from the value itself, right? If the value of skewness equals to 0, that means it's perfectly symmetric distribution. If it's greater than 0, it's right skewed, which is what we have in our case. If it's less than 0, left skewed. Similarly for kurtosis, if it is equal to 0, then it's like normal distribution. If it is greater than 0, which it's in our case, we have heavier tails than a normal distribution. So I think this is everything you need to understand whether alcohol content in the wine is normally distributed. Of course it's not, right? So same here. This looks more normal actually. The pH values, they look more normal visually. And also if you look at the theoretical quantiles versus the quantiles from our data, almost not aligned actually, perfectly aligned except for these high and low sides. So I think I wouldn't apply any transformation to this data. Look at the box plot, almost symmetric whiskers. Median is almost in the middle. So it's again, I would say, mostly normal distributed. But if you look at the values, probably you would get the test statistic is, you see the p-value? Now you see some value right there. Yeah. So it's still not normal distributed. That's what it's saying. Data is not normally distributed because the p-value is above 0.05, sorry, below 0.05. And our null hypothesis is data follows a normal distribution. Now, Anderson-Darling test also, it's not normal distributed. And when it comes to skewness, we are reporting a value of 0.1935, and then the printout says the distribution is approximately symmetric. It's saying that because in our code, if you go scroll above, I set a limit of saying if the data is within plus or minus 0.5, then let's call it symmetric. Let's call it normal distributed. I don't want to apply a transformation. So this is something as an analyst, data analyst, you have control over, right? So you can say that this is approximately normal. It's not that deviating. And same with kurtosis. Yeah, so you can actually define your own limits. So there you go. So you can go through all the other ones, but let's move on to the next piece of code where we look at the non-normal distributions. And again, here I am just plotting a few synthetic data. Like for example, in this case, I have, creating some sort of this is the normal distribution norm.pdf. From stats, you also have uniform.pdf, a uniformly distributed and exponential distributed and log norm distributed and so on. These are exactly the same plots I showed you earlier in the presentation. So let's go ahead and run it for the sake of completeness so you can see exactly how they look like. Yeah. So these are all, and again, uniform distribution has like same value. Okay, now that you know what non-normal distributions typically look like, let's go ahead and find some non-normal examples in our data. How do we find non-normal examples? It's pretty straightforward. You calculate skewness, you calculate kurtosis, and you set some limits, or in my case, I'm basically saying, hey, just print them in the descending order and just show me the top two. So basically, first top two skewness, top two kurtosis, I just want to see what those metrics are, and that's what this part of the code is actually doing. Yeah, it's just calculating this for all attributes and giving me the top 2 attributes. Let's go ahead and run it. Okay, so I should have actually gone through the second part of this code, I guess. Visualize the, okay, this is just visualizing it, so it's not applying. I thought we were applying transformations. I think we saved that for the next one. Okay, examples of non-normal distribution. Here we have chlorides with the highest, and residual sugar is the next one, sulfates, and so on. So histogram of chlorides looks like this, and obviously from here you can tell that this is not normally distributed. Similarly for residual sugar, you have very long tails right there actually. You see some outliers all the way over here, and again from here you can tell that this is definitely not normal distributed. And let's move on to the data transformation part. Okay, we extracted, the whole point, the reason why I did this exercise there is so I can pick which ones I should be working with for the next part, which is data transformation. I don't want to show you transformation on near normal distributed data. Okay, so let's apply this data transformation to our highly skewed attribute. From the previous exercise, we know that it's chlorides. And here again, we are getting the skewness, and I'm finding the most skewed. I'm repeating that exercise again here. And for the original data, where do I apply these transformations? Right there. Log transformation is nothing but log x, right? So it's as simple as that, basically. Applying log of x and just plotting them. That's it. And what are we doing here? Okay, so for whatever reason, my code jumped. So let me go ahead and find where we were. Yeah, applying log transformation. So yeah, this is our original data, and I am just applying log. And log is available in multiple libraries. I'm just using numpy.log, and that's it. And there you go. And some safety right there. I'm just saying c equals to 1 if the value is less than or equal to 0, else the value is 0, and I'm adding the c just to take care of not doing log 0 type of scenario right there. So that's it. And we are calculating the skew and kurtosis and printing them out. And of course, I'm plotting that. And similarly, of course, I'm also plotting QQ, so you can see how the log transform data looks like and how the QQ plot looks like after the transformation. And I do exactly the same thing for everything. Like numpy.square root will give you the square root of those values, and reciprocal is 1 over x, so it's just nothing but 1 over whatever the data is. And box-Cox transformation is where we kind of need to define, again, some safety if minimum value is less than or equal to 0, because that's what box-Cox is like, right? I mean, if it's 0, then it is log of x. If not, it's whatever is defined by this. Right here. So go ahead and apply that, and I think that's all I have. And then I added another transformation right there because again it's available in the package. So go ahead and do that plot, and let's go ahead and run all of these. Everything else is just print statements. So there you go. Now let's go ahead and look at, first of all the text up here, and look at the original data. And this is how the original QQ plot looks like. Now the transform data, once you apply the log transformation, the data looks more normal, still not perfectly normal, but more normal. And when you apply the square root, it's less normal than the previous one, but still better than the original. And when you apply reciprocal transformation, it looks like it's actually much more normal. And box-Cox transformation, and another transformation right there. So these are all the skewness and kurtosis for each of these. Okay. Again, you can go ahead and look at these and see if you made any improvements. In fact, later on, I'm sure I'm doing that in the next part. Okay, quantile transformation. Again, I want to remind you that quantile transformation is where we are forcing the data into certain shape. So here I'm going to show you two. One is forcing the data into a normal distribution and uniform distribution. And there you go. So I apply quantile transformer It's as simple as this. You apply quantile transformer, and you give what output distribution you want out of it. In here, I mean, of course, up here, I'm saying normal. Down here, I'm saying uniform. That's it. And now let's go ahead and run this, and you'll see, let me scroll down, and you should see the original data and the original QQ plot and the transform data. Of course, it's going to be perfectly normal right there, except for that data point. Everything else, and these two, it's perfectly normal along this red line because we are forcing it to behave normal. You will see gaps like these because the data is adjusted such a way that it fits normal distribution. Same with uniform. We adjusted the data such a way that it's uniformly distributed. You have like very similar values, counts, number of counts right there for each of these values. And when you plot it, QQ plot, of course, it's definitely not normally distributed. It's uniformly distributed. And here are some of the skewness and kurtosis results. And you can also see how the transformed values are mapped to the original values. Okay, you can use that to remap back to your original values for interpretation purposes. Okay, so that's it. And I know the tutorial is getting a bit long, so let's go ahead and not dive deep into the results. Of course, you can do that and move on to the next part, basically when to transform data. We already discussed that as part of our presentation. Again, additional notes right here. If you want to go through it carefully, I definitely recommend you doing that. And for the fun of it, I basically said, okay, for residual sugar, let's go ahead and print out a few different ways and few different metrics. For example, calculate multiple normality metrics using Shapiro-Wilk, skewness, and kurtosis, and a few others, and also plot a few and compare them and display the data in a table format so we can decide, okay, which of these is the best way, or the best transformation for it to be normally distributed. So all this code is basically doing exactly that. So wine quality, you're looking at the residual sugar. This is the original, and this is the log transformed with Shapiro-Wilk value, right there. But more importantly, you can look at your original data, log transform data. Is there any improvement? If yes, we can probably use one of these. Excuse me. We can probably use one of these transformations for this specific data. Okay, I think that's the end of it, and remaining is just some notes for you to go through so you can keep this notebook for future references. The key point, again, I want to end by saying that in the next tutorial, we are going to move on to actually comparing two groups. So far, we looked at various attributes within one data set. Now, let's say you have two groups of data that you are trying to compare. What type of parametric tests? And this is where we'll compare like means between two groups, like using tests like t-tests, and how to interpret the results. And for that, we are going to go back to the UC Irvine heart disease data set. And I hope you're excited to learn about, the topics about t-test, for example. So please come back, and I'll see you in the next tutorial. Thank you very much.